Hello and welcome to session 10. Today we are looking at exponential and logarithmic functions. So can you see my screen? Just double check. And in the meantime, while we're doing that, let's answer these questions. So warm-up questions. Can you find the value of y? I'll zoom in a little bit more. If you can, without using a calculator, what are the values of y? And if you answer that, then I know you can see my screen. I hope so far all of your exams that you've had have gone well. I think there's been business and physics. Hope they've been going nicely. Still a week and a bit until maths, so got time. Any idea? Log 5 of 25, log 3 of 1. What is the value of y? You can just answer one of them or all of them. If you don't want to answer that question, could you just confirm that you could see my screen? And if anyone is new here, awesome. Thank you for applying. I have my iPad over here with the chat function, so I can see it there. So if I keep looking over there, that's because I'm looking at the chat. All right, let's go through it. And again, in case you're new here, I'm Ashley from Miss IB Maths, collaborating with Exam Dojo for these bootcamp sessions. So this will be our 10th session, and we have another couple lined up over the next few days. And all of the notes and exam questions are in a folder. If you would like to see those, you can just DM me at Miss IB Maths on Instagram, and I can share with you the folder. All right, let's get into it. So when we have base 5 of 25, we want to know what y is. You can think about it like answering this question. 5 to the power of what gives me 25? So there we can see that it is going to be 5 to the power of 2. So y equals 2. Here, y, and if I zoom in, sometimes I find it helpful to think of it like this. If you add a little block here, 3 to the power of what gives me 1? Well, that'll be 3 to the power of 0 gives me 1. So y equals 0. Here, 16 to the power of what gives me 4? So we know that 4 to the power of 2 gives me 16. What about 16 to the power of what gives me 4? That's just the inverse. So 16 to the power of a half gives me 4. 16 to the power of a half is saying root 16. It's the same thing. So y equals a half. That's a bit chunky. And 2 to the power of what gives me 1/8. So you may know that 2 to the power of 3 gives you 8. So if you want 1/8, it's going to be -3. 2 to the power of -3 is going to give me 1/8. So y equals -3. Just a little warm-up of what logs mean there. Just the inverse of our exponents. And if you forget that, luckily it's in the formula booklet. So this is what we have in our formula booklet. As I always say, it's a good idea to have this open next to you when you're answering a question, say your questions on exponents and logs. Then have this page open next to you, because it's really going to help to be able to see what you have to work with. They give you quite a lot here in AA. In AISL, you don't need to know log laws. You only need to know how to change between exponential form to log form or vice versa. So that's all you need to know for AISL. Everything else will be done by the calculator. But if you're in AA or in AIHL, you need to know these log laws. So we have the log laws that if you are adding two logs with the same base, the key with logs is the same base. We can only do operations when the bases are the same. Same with exponents. When the base is that little number in the bottom there, the a is the same, and we're adding logs, we can also say that we multiply them within the same log. Likewise, for subtraction, that becomes division. This is a very useful one. This comes up a lot, that if you have like log 2x to the power of 2, for example, this power over here, you can move it to the front. That's a very useful thing, or move it back from here onto there. So this is also 2 log 2x. So this one actually ends up coming up quite a lot. Then we have the change of base formula. They don't tell you it's the change of base. You just need to know that. And this comes up quite often in AA, that you need to change the base. You'll have, say, a log 9 of something and a log base, say, 3 of something. And you'll need to change the base of one of them so that you can work with them both. So I could change this log into a base with 3 so that I can perform the operations with base 3. And then for our natural logs, you can turn any exponential function into a power of e function. So it's quite small. Let me zoom in. There we go. So if I have, say, 2 to the x, I can change this into an e function by saying e to the x natural log 2. That base there, I can just put with a natural log 2. And then having that, I can change any function into a power of e function, which is very useful. Again, that's just for AASL and these log laws for AIHL. And AISL just need to be able to change between logs and exponents. All right, so let's just quickly have a look at our exponential functions and some properties of them. So if we have a fixed base a, the conditions are that a needs to be positive, more than 0, and a does not equal 1. So 1 to the power of x is not an exponential function, because if I have 1 to the power of anything, it's just 1. So that's just going to form a straight line. I also cannot have something like minus 2 to the power of x. That's also not possible, because my a must be positive for us to have that exponential growth or exponential decay shape. What I can have, though, so that's, let's put a line through that. So can't have that, but what I can have is negative 2. See that my base is still a positive number 2, I've just reflected it. So instead of going like this, it's going to go like that. It's being reflected, not to be confused with exponential decay, which is when I have a value of a that is between 0 and 1. So let's say that this graph could be something like 2 to the power of x or e to the power of x. This function would be something like a half to the power of x. So it's a value between 0 and 1. So just a couple of things there. If it's going up like this, we call this exponential growth, but if it goes down like this, we call it exponential decay. So key features of an exponential function. One is the horizontal asymptote. So the parent function, like before we've done any transformations on it, say 2 to the power of x, will have a horizontal asymptote of y equals 0. So it never goes below the x-axis. So that dotted line there has the asymptote, and then it will keep continuing upwards. And important to note when they ask in the exam for what is the equation of the asymptote, it is very important that you don't just write 0. 0 will get 0 marks. You have to write the equation. This goes for all asymptotes. They will always say, what is the equation of the asymptote? And you must write y equals 0 or x equals 0 if it's a vertical one. But for our exponential functions, we have horizontal asymptotes only. Another key feature is the y-intercept of 1, because if you think about all functions, 2 to the power of x, e to the power of x, 5 to the power of x, 100 to the power of x, any time that number is 0, that x is 0, they're all going to give 1, because anything to the power of 0 is 1. So all of our exponential functions, parent functions, before any transformations, not 5, that was 100. No matter what they are, they're all going to go through the point y equals 1. Then, of course, we can sometimes have the transformation where we have 2 to the power of x plus 5. And then you know that it's just going to be 2 to the power of 0, which is 1, and then lifted up 5. So it will go through 6. For the domain of an exponential function, it's all real numbers. So it goes all the way that way, all the way that way. We have all real numbers, nice and easy, negative infinity to positive infinity. The range, however, goes from the horizontal asymptote. So this one, the horizontal asymptote is y equals 0. So our range for this one is going to be from 0 to infinity. So wherever that is, it's going to be any values upwards, right? If we had the function that goes like this, that way, it's going to be wherever the horizontal asymptote is, let's say 0 again, to minus infinity, because it's going all the values down that way. So if we know our horizontal asymptote, we can figure out the range of our exponential function. You are welcome. All right, then we have Euler's number, E, the E function. Nothing too crazy that you really need to know about the E number. Just don't treat it as a value E, treat it as a function E. That's something that I often see students doing, is getting confused with having the function of E and the number E. So anytime you see E to the X, we're talking about the function E, and it's going to have, it's also going to have the exponential function shape. So it also has that, look, it also goes through 1, and it also has a horizontal asymptote of y equals 0, and that coordinate of 1. So it's just the number 2.7. So not very different from the function 2 to the power of x, which is that number 2. This is just 2.718 to the power of x. But this E does special things, and that could be an interesting IA topic, but you guys are done with IA, so never mind that. But for now, all you need to know is it's just a normal exponential function. And it has its own inverse. So any functions that we have, like a to the x, have their inverse functions, log, which we're going to look at, a of x, just like e to the x has its own special inverse function, which is natural log of x. And what this is just log with a base e instead. So instead of that a, we have log base e. So these are the same thing. But we give it a special name, natural log. Just like e is special, its inverse is special. So let's say we are sketching a graph. If you're AISL, you can just do this on your calculator and copy it. Let's see. Nope. Let's try that again. Let's do it in black. There we go. All right, so if we're sketching the graph, the first thing we want to do is find the horizontal asymptote. So the horizontal asymptote, remember, if it's just this function 2 to the x, then our horizontal asymptote was y equals 0. But now we've shifted downfall, so our horizontal asymptote becomes y equals minus 4, because we went from 0 to minus 4 down, so that gives us at minus 4. And shortcut, it's just whatever that number is your horizontal asymptote. Because if you think about it, 2 to the power of x is just plus 0, so that gives you your horizontal asymptote. So if we plot that at y equals minus 4, let's do like here maybe. This is the line. Always draw asymptotes with dotted lines and label them. So y equals -4. Great. Then find the y-intercept. So substitute x equals 0. So let's substitute x equals 0 in here. 2 to the power of 0 minus 4. Well, that's just 1 minus 4, which gives us -3, which makes sense. The intercept is always just 1 above your horizontal asymptote. So say 3 is there. Sorry, -3. -3 is there. Right, then find the x-intercept. If there is one, there isn't always an x-intercept. Sometimes your graph will go like this, just above. So it doesn't actually go through because the horizontal asymptote is at the x-axis. But this one's been transformed, so it probably does. So we set 0 equal to y, and then we solve to x minus 4, solving for x. So I'm going to move 4 to the other side. 2 to the power of what gives me 4? This one's nice and easy. So x equals 2. So when my y is 0, my x is 2. There we go. And now we have 2 coordinates, which help us to plot an exponential function. We have our asymptote, and we know it's got a general shape like this. So we're just going to fill that in. Let me take away this for now. And maybe that, I don't want to confuse people who look at the notes later. So, let's see if I can do this nicely. It's going to go through there. And, okay, this is a very ugly graph because I'm drawing it on a sketch pad. It would have a smoother shape, but there we go. And it's not exactly accurate because that was 2. But if they say sketch, it's okay to have it quite roughly. So if they say in the question graph f of x, the word graph means it has to be exact. It has to be really specific, and they'll usually give you grid lines for that. If they say sketch, then it's just rough, a rough sketch. So you don't need to do like 1, 2, 3, 4, 5 and really make sure it's super exact if it's a sketch. So, and you'll usually see it's not worth many marks. But if they say graph, then it should be as perfect as possible. Right, so now we have the very ugly graph of f of x. I'm just going to write f of x next to it, label your intercepts 2 and -3, and label your dotted asymptote line. And there we go. That's a sketch of the graph. All right, so as we're saying, we have the inverse of exponential functions. So if this red line, that's my exponential function, then the inverse function, exponential, is my log function. And it's all inverses are reflections around the line y equals x, all inverses. That's the line going through diagonally through the origin. So this is my exponential. So just reflected over that line gives me my log. And what we know about inverse functions is x becomes y becomes x, domain becomes range becomes domain. They just switch. So all of the things that I had happen for my exponential function are now going to be the opposite. So in my exponential function, I had the asymptote of y equals 0. So my log function, I'm going to have the asymptote of x equals 0. So you can see here the line y equals 0. That was my asymptote for this function. And now for my log function, this axis becomes my asymptote. So we've switched them around. And then do you remember that we had the coordinate of 0, 1 was where this one went through. That was the main function. And now for this one, it's going to be 1, 0. See how they just switch places? Because they're opposite. So it goes through 1 over there. Here, 1 on the y, here, 1 on the x. Everything just switches. So a couple of things about the log function that we were just saying. You can have it be increasing, looking like that. This is kind of the standard function with our asymptote of x equals 0 going through the point 1. And decreasing if we have something like log half x. when you have something that's a fraction, a number between 0 and 1, it's going to be decreasing like that. And like I mentioned, the key features, we now have a vertical asymptote. So you're going to say x equals 0 or x equals whatever the asymptote is, and an x-intercept, not a y-intercept. And again, domain and range switch. So do you remember our domain for our exponential? This is a bit of a revision on inverse functions as well. Domain of our exponential was minus infinity to infinity. And now that's the range because they've swapped places. This is for our log functions. And the domain is also similar, except we just have it within here. So for our exponential function, we had wherever the asymptote was, that was our domain. That was whatever number was added or subtracted. Let me just write that. X plus, let's say, k. So that became our y asymptote. So now it's the same thing, except it's within the function because it's x and it's going to shift it. So if it was log x minus 4, then we're going to have an asymptote at x equals 4. So it's just that value. Note there's the minus already in the equation. So when I'm taking this, it's just positive 4. And so it'll be whatever value is more than that, is more than 4. So they just switch like that. And our natural log, we spoke about this a little bit before. It's the same as log base e of x, but it has its own fancy name. And they are the special inverses of each other. And change of base formula for, we can turn any function, log x, just like we could turn any a to the x function, we could turn it into an e to the x function with this little formula. We can do the same with a log. We can change any log function into an x function. So let's say I have log base 2 of x. Well, that just becomes natural log x over natural log 2. So it's very similar here. Let me do that one as well. Let's say 2 to the x is e to the x and 2. This can be useful if you're wanting to convert a natural log function into a normal log or other way around, depending on your bases. So let's do a sketch of a log function. So we have, let's go with now green one. So same method. The vertical asymptote is at x equals h. So this number here, the positive one. So we have x equals 1. This is our vertical asymptote. Again, dotted line and label it x equals 1. Just going to remove it there because I've already written it. Then set it equal to 0 to find the x-intercept. So set this equal to 0, log 2x minus 1. And now some log laws. In order to solve something with log, I need to have log on the other side so that I can get rid of it. So I need to turn this 0 into a, let me go down a bit so I have up here. I need to have log base 2 of something that's going to give me 0. So if I have, think about what value, like when that's 0, I can just do, let's say, 1. 2 to the power of 0 gives me 1. So I've changed this 0 into a log. Because remember how we had at the beginning, you need the 2 to the power of what gives you that number over there. So now I've changed my 0 into a number that has a log with a base 2, excuse me. So instead of 0, I'm going to write log base 2 of 1 equals log 2x minus 1. Move over a little bit. I might be out of the screen here with my video. If you can't see, let's do like that for now. Maybe I'm actually going to move this a bit out the way. All right, and now hopefully you can see. So all I've done here is changed out that 0 and made it a log base 2. Now that I have log base 2 on both sides, I can drop the logs. So if I drop the log, I'm left with 1. And if I drop the log here, I'm left with x minus 1. So add 1 to this side, so x equals 2. So now I know that my intercept there is at x equals 2. Okay, now with our log, we need another key point. So I need to find another value of x that's convenient. That means like a nice number to be able to plot it. So if I see my function here is log base 2 x minus 1, I need to think of a nice number here that I can get. So I'm going to think 2 to the power of something that could give me that number. So let's say 2 to the power of, I don't know, 3. Random number. 2 to the power of 3 would give me 8. So this thing, when I need that to equal 8, that would make x equal 9. Let me just write that again. Log 2, 9 minus 1, that's going to give me 8. Log 2 of 8 is just 3. So that's a really nice coordinate. 2 to the power of 3 gives me 8. So I can have my x as 8 and my y as 3. So that's a nice coordinate. I could have used any others. I could use maybe 5. 5 minus 1 gives me 4. So that would be 2 to the power of 2 gives me 4. So when they say a convenient x, they just mean something that's like nice and easy to calculate by hand without a calculator, if you don't have one. All right, so we're going to have 8. Let's say 8 somewhere here, and 3 maybe is somewhere there. And now I can draw my function. So let's go. It's coming up along that. Ooh, come on, there we go. So there we go. It is going along my asymptote, but not quite reaching, and all the way that way, making that arc shape. So that's how we can graph a log function. All right, let's get on to some exam style questions. If you have any questions, or if anything I've just explained didn't make sense, please let me know. I'm going a little bit over working with logs and log laws and things like that in this, but if you want a full session just dedicated to working with log laws, I think we have space for one more session. So let me know if that's something you'd be interested in. Okay. A lot of the time, these questions come up in paper 2 because you just need to take the very complicated looking function that they've given you, put it on your calculator, and then graph it. So the only thing that becomes, or not really difficult, but that students miss out on is the domain, which actually makes your life a lot easier. So can you see they want it between -2 and 2? On the graph, they've given us between -2 and 2. Sometimes they might be a little bit tricky and they might give it to you between like -4 and say 6 or something like that. And so if you draw the graph, however it looks, and you go outside the domain that they gave you, then you don't get the marks. So it's really important that you look at the domain, look at the graph they've given you, and make sure that you sketch only the domain that they want from you. This function, you don't need to know how to graph yourself. You might look at that and think, oh my gosh, we never studied that. Anytime you see a complicated function, you are most likely going to find yourself in paper 2, and then use your calculator. Just don't even try think of it. You don't want to make any mistakes. We're going to input the window, so it's exactly like this. All we do is just copy exactly what we see off the screen. So let's put that in. We have e to the minus x squared minus 0.5. So I'm going to go graphing. No, I want file. I'm using a TI Inspire. If you are using a different calculator and you're not sure what buttons to press, again, you can just send me a message at Miss IB Maths on Instagram and say, how do I do this on my calculator? And I will happily do a little video or explanation for you. So we have E, and now I need the graph of E, not just going to type E. Negative x squared minus 0.5. Be very careful when you're graphing that you are graphing the correct graph. So let's see, what is that? Okay, and I'm not going to copy that yet because they said my domain is between -2 and 2. And a little hint, they haven't said my range, but they've only given me between -2 and 2. So I'm also going to add that to my window. So I'm going to say menu, window zoom, window settings, and I'm going to change this to -2 and 2. So it's going to show me exactly what I need to graph without even having to think about it. If they haven't given you a graph with the minimum and maximum of the y, that's okay. There's no limit there. It's only the x they've limited, but because here I see they've given -2 and 2, I'm just going to make my life nice and easy. All right, and then we've got the graph. That's all I need to do, but still make sure that it's accurate. So the graph is going here, there's 0.1, there's -2, so -1 is about there. So I need these endpoints to be a little bit above -1. So if my -1 is there, then I want my endpoints somewhere here and here. Then 2 is there, so 1 is around there. So this maximum looks like it's at about 0.5 over there. Oops. Somewhere like that. Anything else? Here are my x-intercepts. These should be quite accurate, and I've skipped a question. They said find the values of x for which f of x equals 0. So let's do that because it'll help with our graph. So this is saying when does the function, when does y equal 0? When are the y values? That's here. When are the y values 0? Those 2 points. It's another way of saying what are the x-intercepts? So I'm going to go menu, analyze graph, and I want the zeros. Zeros are where it hits the x-axis. Zeros could also be called solutions or roots or x-intercepts. On our calculator, it says 0. And our calculator is not very smart. We've got to give it a lower bound and an upper bound. And there we go. Minus 0.833. 3 significant figures. 833. So we can write x equals 0.833. Say x, my x1 and my x2. I have another one over here. So let's go again. Analyze graph. I want my 0 at this point. It doesn't need to be any particular distance. 0.833. Look at that. Perfectly symmetrical. So that was negative 0.833 and positive 0.833. And seeing as you're reading it off the graph, there's no calculations to be done further, just 3 significant figures is good enough. Okay, so for my x-intercept, I have it at minus 0.833. So that's just before 1. So they're going to be checking that since you figured this out, you don't put your x-intercepts somewhere there. It has to be before -1 and before 1. So somewhere like that. And now just check my shape one more time. It's a nice sort of wave. So let's follow that. Let's go. All right, there we go. Should maybe have a bit more of a dip, but that will do. And that is a lovely 3 marks. They will give you a mark for having correct, well, let's go and have a look at the mark scheme actually. Well, they haven't said, but let's just check. There we go. Minus 0.833, 0.833. You get 1 mark for each correct one. You don't get marks for having said the full amount of decimal places. It's not wrong to do that, but make sure that you do have 3 significant figures. And the 3 marks here, they would give for having the maximum at the correct place, having the intercepts at the correct place, and having the endpoints at the correct place. So the graphs usually work on those things. And there we go. That was a delightful 5-mark question. My biggest advice to you when you see these log questions or exponential questions is don't let them scare you. Okay, they look crazy. They look a bit like, oh my gosh, what are these functions? When you look at them, especially when you look at the question, there's just a lot of things going on. But they're always going to have the same sort of just use the equation, graph the equation, input your x, get your y. They just want to check that you know what your input is and your output is. So as usual, I always say, bring highlighters into your exam. Bring highlighters, bring different color pens so that you can mark off things in the question. So I'm going to mark off my input. So the loudness of a sound, L, so that's my one variable, measured in decibels, is related to its intensity. I'm going to use a different color. Intensity, I. So these are my two variables. So if I look at my function, my output is L. So I'm just going to write on top of that Y, because we're used to X going in, Y coming out. If you have that, then you remember which order you need to be going in. So my output is Y, which is L. Loudness of a sound. What we're trying to find is the loudness of a sound. Then that means intensity, that I over there is my X. So that's all it is. So when we're reading questions, we're just figuring out what is my X, and it's going to give me my Y. And we have this lovely function with base 10. Just another note, I don't think I said it before, if you have log, say, of X, if there's nothing written there, it's assumed that it's base 10. We just don't write base 10 all the time, but here they've written base 10. So we have two sounds, S1 and S2. S1 has an intensity, an X value of 10 to the minus 6 units. Now, don't immediately think that you need to go and change this to like 0.000. Just leave it like that. We can work with exponents. It's probably going to be easier if we leave it like that rather. Also, it's a paper 2, so calculator is allowed, so you don't need to go and change it. So S1 has an intensity of 10 to the minus 6 units. So that would be our X. Let me just highlight that in blue. And a loudness of 60. So that's my output. 60. I input 10 to the minus 6 into this, and I get 60. S2 has an intensity that is twice that of S1. So an intensity, just going to highlight, that's our X, twice of S1, okay, twice that. State the intensity of S2. So the intensity here is twice that, 2 times this. So they just want me to write, ooh, that's not the right pen, jeebus. S2 is equal to 2 times the intensity of S1, which is 2 times 10 to the minus 6. And I can leave it like that, so only with 1 mark. And this isn't necessarily any less simplified than 0.000001. So leaving it like that is absolutely fine. Determine the loudness of S2. So we want to figure out if the intensity of the input is this, what is the loudness? So let me go again with that. This is my input, and I now want the loudness, the output. All right, so let me write this equation. We have L equals 10 log base 10 I times 10 to the power of 12. And they're saying that my input is 2. So 2 times 10 to the minus 6, that goes there, right? That was my I. So 10 log base 10 of 2 times 10 to the minus 6 times 10 to 12. I can put this entire thing on the calculator because it's a calculated paper, and that way I'm less likely to make algebraic mistakes. The question, is this an exam style question for AI? Yes, you could have questions where they ask you to input certain values. So the only thing that you won't have to do is these kind of questions in paper 1, where sometimes in paper 1, you will not have a calculator, so you'll need to use log laws. But in AI-SL, there are questions where you would need to input certain values, because all we're doing is substitution. We're substituting this into this, and we put the whole thing on our calculator. So in that sense, that's an appropriate question for AI-SL. So let's put that all in on our calculator, although you might have seen 10 to the minus 6 times 10 to the 12 is 10 to the 6, because our exponent law is minus 6 plus 12 gives us 10 to the power of 6. So 10 log 10, let's open up a new document, file, new, no, I wish there was a quicker button for that. I mean, there's Control N, but you still have to do the whole save thing. So we want 10 times, and we go Control log base 10 of, what was it, 2 multiplied by 10 to the power of 6. Just simplifying my log laws there. Again, you can type out the whole thing and not simplify that. That'll be fine. We get 63.0103. I'm going to write out the whole thing. 63.0103. Double check I carried it across. Right. Okay. And don't forget 3 significant figures to show that you've rounded. So you don't just put 63. That's not 3 significant figures. It needs to be 0.0. That's 3 significant figures. Even though it's 0.0, you think, well, what's the point of writing 0.0? That just means 63. But if you write 0.0, you show that you have rounded an answer, because 63, that answer, is very different from this answer. So we do need to show we've rounded. So 63.0. Right. That was 2 marks there. The maximum loudness of thunder in a thunderstorm was measured to be 115 decibels. So loudness, which variable was that? Loudness was my Y. Where's my yellow? Loudness was 115. So that's my output. So I'm going to have to work backwards. So let's write my whole formula. 10 log base 10 I times 10 to the power of 12. And now we're doing loudness is 115, and we're working backwards to find intensity, or I. So to solve this in AI-SL, you probably won't have a question to solve like this. This is a bit complex, but what you would do, and this can apply to other kinds of questions when you need to find and work backwards, you plot the line y equals 115, and in fact AA can do this as well, because you also have a calculator in this question. You plot the line y equals 115, and you plot the line 10 log 10 I times 10 to the power of 12, but you use x instead because your calculator only recognizes x as a variable. You graph both of these lines. This will just be a straight line like this. This will be a log equation, and let's say it goes like that. You just find their intersection. That can work for any one in which we need to work backwards. But let's say that we are... Well, we're 3 marks in a paper 2 question, so I might do that rather than solving. But anyway, let's show you how we could solve. We can divide by 10 on that side, equals log 10 I times 10 to the power of 12. And now let's convert this, because it's good practice, from log form into exponential form. So exponential form would say that I have 10, because that's my base. Let me highlight that. It's good practice. My base 10. To the power of, this is now my power. In fact, let me not use that highlighter to confuse you. To the power of 115 over 10, this is just one of our conversions between log and exponentials, is equal to I times 10 to the power of 12. And 115 divided by 10 is just 11.5. Should have done that earlier. We can divide it by 10 to the power of 12. And that gives me my I. again, this you can put on a calculator, but by my exponential laws, because it's great to practice, 11.5 minus 12 gives me minus 0.5, which is 1 over 10 to the power of 0.5, which is 1 over root 10. All of this that I've just done was just practice on, let's say from here, practice was showing you some exponential law practice, but don't worry, you can just put this straight on a calculator and you'll get 1 over root 10, or you can get it in its exact form. What is 1 divided by root 10? 0.316. So I equals 0.316. And again, you can go straight from that to figure that out. Okay. Let's have a look at the mark scheme. Any questions? No. So see here, you get the answer just for earlier, writing it as 2 times 10 to the minus 6. If you did happen to convert it into standard form or normal number form, that's fine. It's not a problem, but you don't have to. Then substituting, you get a mark from whatever value you had in A. So if you got A wrong, that's okay. You can still get the marks here if you use your I value. So that's a good thing to continue with questions. Just because you don't understand the first question doesn't mean that you won't be able to answer second or third questions. Then we have attempts to solve. So here it was 0.316. Did I write 0.316? 318. Whoops, I wrote that incorrectly. Double check as I keep saying that you copy it across correctly. So we have 0.316, but you also get for 10 to the power minus 0.5 or 1 over root 10. So those are also acceptable answers, and you'd still get 1 mark each for those. So either is fine. Okay, another question. This is a paper 1 question. So this is no calculator allowed. So everything here we have to do algebraically. So this is one point where I would say AISL, you don't need to know this. There's going to be some log laws in here. I think most of this would be not relevant to you. This is our last question. So if at this point you are not wanting to continue on, then that's fine, because it's not relevant to you. I can finish it off for you. We would answer that question, just going through, and then have some exam tips as usual. So, sorry, this is just for AISL who might want to leave at this point, seeing as the last question isn't for them. Always state the vertical asymptote as an equation, as I said, x equals 0. The x-intercepts and y-intercepts of our log and exponential are really good to memorize. AISL, you don't need change of base or that. So that's it. And the notes are there if you want to go through them. And there's a homework assignment. Okay, that's what's for AISL. Now, if you're AA or AIHL, let's do this question with no calculator. For AIHL, even though you have your calculator, you still can get asked to do these kind of questions to be able to use log laws. So this is still relevant for you. And you are most welcome. So we have 2 functions, ln 2x minus 7, where x is more than 7.2. So I'm just going to highlight that because sometimes questions we can get answers that we might have to disinclude. Is that a word? Exclude. We might have to, this is what happens when you live in a country that doesn't speak English. We may have to exclude some solutions based on this domain. So let's just highlight that, and let's highlight that. X is more than 0. D is an element of positive real numbers. Write that. Positive real numbers. So definitely think later on we're going to get a value that's a negative number, and we're going to have to show that we saw that. And our second function is 2 ln x minus ln d. Or natural log if you say natural log. So this might confuse you. You might think, oh my gosh, what is that? That's just a constant. D is a real number. So D could be 2. It could be ln 2. And if you put that on a calculator, that's just a number. Like, let's see what that number actually is. Natural log of 2, which is some very ugly number. 0.693147. So we're just subtracting a constant. So that's not actually part of the function. This would be the function, and we're just subtracting. This is how much we've shifted up or down. So don't be scared by that natural log d. It's just a constant. Now, state the equation of the vertical asymptote to the graph of g of x. So, just like we were saying here, where x is more than 0, vertical asymptote. For a log function, remember, let's just draw it. Sketching it quickly sometimes helps us to remember what we're doing here. Something like that. So all of the, I shouldn't actually do this one with a dotted line because that is confusing because we have asymptotes with dotted lines. That's the graph. Our asymptote, let's put our asymptote in red, of a standard function was at x equals 0. So they want the vertical asymptote of this graph. And we have to think, well, that was when it was in the form x minus h, when we were moving it left or right. But in this one, have we moved it left or right? Because remember, this part is outside of the function. That's not within it. So no, we haven't moved it left or right. This is moving it up or down, not left or right. So it's the same as saying this is 2 natural log x plus 0 minus natural log d. So x plus 0 there. Nothing has actually happened. So it is still x equals 0. Well, that was a lovely easy mark. X equals 0. I think they're trying to confuse you with the natural log d. The graphs of f of x and g of x intersect at two different points. Show that at the points of intersection, we have this value. Just remember, in a show that question, you cannot use this in your answer. You have to end with this in your answer. Anytime it says show that, you need to end with that. You cannot use it. Pretend you haven't even seen it. And then when you get to the end of your answer, you can be like, oh, does it look like that? If it does, great, you're done. If it doesn't, try and have a look for where you might need to be able to get to that. So let me start writing down here. So we want to find the intersection. Anytime you're finding intersection, that means you're setting the two graphs equal to each other. So intersection happens. Intersection is when one graph is set equal to the other, and then we solve for the values of x in which that happens. So we're just going to put them equal to each other. So I have natural log x. No, write my thing down wrong already. Natural log 2x minus 7 is equal to 2 natural log x minus natural log d. I say ln for natural log just because I had teachers who said that. So now it's stuck in my head, but I know a lot of people say the whole natural log. So if I say ln, I mean natural log. Right. Now, I've set them equal to each other. I need to solve for x. Don't worry about the fact that I don't know what d is. See that there's d within the answer. I'm going to treat this d just like a normal number. Don't be scared about the d. When I'm solving log equations, I need them to all be in this form. Log of natural log of something equals natural log of something. Once I have them in their neat little brackets, I can drop the logs. I can essentially cancel them out on each side and just have those things to solve, which is way easier. So I need to get all of the stuff that's around them within those brackets using my log laws to be able to drop them. So I can't even have something like in the front there. That's not enough to be able to drop them. Must have nothing around them, just log and then everything else in their neat little bundles. So this one's fine. That's in its neat little bundle. This one over here, we're going to need to do some log laws. Now, a common mistake that I see students doing is putting like this, 2 ln x over d. But you can't do that because there's a 2 outside. We can't bring those together with that 2 hanging out there, because now I'm saying this 2 is applying to that d as well, but that's not true. The 2 is just for that x. So the order here is important. I need to get rid of this 2. And do you remember our rule that if you have a number in front here, you can bring it to an exponent over there. So I can write ln x and bring that squared there. Okay, minus natural log d. And that, now that it's in there, now I can use the subtraction law, which is to divide them. X squared over d. There we go. And now it's in a neat little bundle. Great, that's what we wanted. And now I can drop, cancel. It's not exactly what's happening, but that works for us. I can drop my natural logs. Just go in blue. So we have 2x minus 7 equals x squared over d. See how we're starting to get more into these terms. Now I have a d in my denominator there, so I'm going to get rid of that by multiplying it on the other side. So I'm going to have 2dx, because that gets multiplied by d, and this is going to get multiplied by d, minus 7d equals x squared. Getting closer and closer to this. This one says I need to make it equal to 0. So I'm going to move everything over to the side. So I'm going to have x squared, oops. X squared minus 2dx, because I'm moving it over. So positive 7d equals 0. All right, so I've shown that at the points of intersection, that is true. X squared minus 2dx plus 7d equals 0. We can't really solve because we don't know what d is, but we have shown that at the points of intersection, that is your hint. Points of intersection, if you see that at all, put your 2 graphs equal to each other. Anytime you hear the word intersect, intersection, points of intersection, take your 2 graphs, set them equal to each other, and then solve and see where you end up. You don't even have to read further. Definitely read further, but remember that. That was BI. And we had AI answered there. Hence, another important exam word, hence. This means use something that you have before. Hence, show that d squared minus 7d is more than 0. That means whatever you've calculated before, you need to use that somehow. And if you're not using that thing somehow, then you're not answering the question properly. There may also be other methods to solve that question, but you need to use what you've just calculated to get the marks, not some different method. So hence show that d squared minus 7d is more than 0. Now, a hint here, when we see more than 0 after a quadratic equation, we need to think discriminant. Discriminant is something that is tied to the quadratic formula. The quadratic formula is, I'm going to go on a little tangent here. So let me write this on the side. Let's go in green so we know we're on a tangent. If I have a quadratic, let's say x squared, let's do the full thing, plus bx plus c equals 0, and I'm solving for x, and I have the quadratic formula, b squared minus 4ac over 2a. The discriminant is what's happening underneath this square root sign. So we take that b squared minus 4ac, and that's really important, this part, in what happens with my x values. Because if you think about this square root, whatever this value is that I've highlighted, if that is negative, if that whole thing is less than 0, well, you're going to have no real solutions because you can't have negative numbers. So if you get that the discriminant is less than 0, there are no real solutions. If you're in HL, there are imaginary solutions, but no real solutions. So we get some complex numbers there. But for us, no real solutions. If my b squared minus 4ac, if that whatever is in here is equal to 0, well, then I just get root 0, which is 0. So the positive and negative 0 just mean that you get one solution. So then we just have one real solution, or one distinct solution. If b squared minus 4ac, and this is the case we see more often, is more than 0, we're going to get our positive value and our negative value. So we're going to have two real solutions. So what they're saying here, after we've done this one, we've got our quadratic, and they're saying, when are the values here more than 0? That's our hint that we're using this one, more than 0, when b squared minus 4ac is more than 0, when we have two real solutions. Because they said they intersect at two distinct points, two real solutions. So let's go and answer that. We want when the discriminant is b squared minus 4ac is more than 0. So what was my quadratic? My quadratic was x squared minus 2dx plus 7d. So my values, because remember we have the values of a, b, and c. What are they in here? Well, my a is 1, my b is minus 2d, and my c is 7d. Because whatever d is just going to multiply with that number to make a constant. So b squared was minus 2d, and then squared. Minus 4a was 1, so I'll just write that to be clear. And c was 7d, is more than 0. So if I solve this, I have 4d squared minus 4 times 7 is 28d is more than 0. And I want to show that that equals that. Well, that says d squared, and here I have 4. Here says 7, and here I have 28. But I can divide these all by 4. So then I get d squared minus 7d is more than 0. And there we go. I've shown that it is equal. So that's just a hint that if you see after a quadratic things that say more than 0, less than 0, equal to 0, you're probably heading in the direction of the discriminant. So you're using that. It comes up more than you think. And now that we've done that, this is still part of the question, part of this. Find the range of possible values of d. So I'm going to use this, d squared minus 7d, to find the possible range. They say range because it's more than 0. I know that d is more than 0. So there's certain values it can be. I'm not going to find what it's equal to, but I'm going to find a range of values that it is. So d squared minus 7d, that is a quadratic. Let's do a little sketch. This is not perfect. Let's just say something like that. That's my quadratic, d squared minus 7d, going through the point 0 there. Then I want to know, when is my graph of d squared minus 7d more than 0? So when, oh no, it's not going to be exactly like that. It's going to be more like, this is a very rough sketch, but it's going to do what we need it to do. When is it more than 0? Well, when is this graph more than 0? This part here is when it's less than 0. So we want to know this part. That's more than 0, and that's more than 0. So at these parts, we have the value of d is more than 0. So let's figure out what are our x-intercepts there, and then we can find those values that it's more than. So d squared minus 7d, let's write that here. We need to set it equal to 0 to find out what those values of d are. So we can factor out d and have d minus 7 equals 0. So d equals 0 is one solution, and d equals 7 is one solution. Now, this is where you can see my graph is not accurate. Maybe I can take away my axes. Don't want to confuse people. It'll be something like this. So my value there of D is 0, and here is 7. So when is my graph, for what values of D is it positive, basically? More than, it's above the x-axis. So when D is less than 0, and when D is more than 0. So that's the less than 0 part, that's the more than 0 part. This is just in general how we solve, or one way to solve inequalities with quadratics, to use a sketch. It just makes a lot of graphical sense. And there we have our solution. This is the range of possible values of D. D is less than 0 and D is more than 7. But when you finish your answer, go back and check your question and just double check, did we have any restrictions? Well, can you remember that D is positive real numbers? We can only have positive real numbers. So let's check. D less than 0, that's not a positive number. So that's not a solution. So it's only D is more than 7. That was our only value. Okay, so I think we will stop there because it's up to 12. I'll have these notes if you want to continue with these questions. It's quite a good question. And you can send me your solution, or if you want a solution. But I will stop there for now. And yeah, just remember to always state your asymptotes as equations. X equals 0 or Y equals 0, not just the number 0. That is easy points that you can get, easy marks, 1 mark for each. And if you don't show the X or the Y, it's wrong. Even saying vertical asymptote equals 0 is not appropriate. It must be an equation. And you need to show that you know that vertical is the X and horizontal is the Y. Change of base formula is given. You can use that when you need to change between things. They give you quite a lot in the formula booklet for AA especially, and for AIHL. And yeah, I think that's everything. Notes as usual are over here if you want them to go through these things. And there's also going to be a homework assignment on this session. So there'll be some questions you can practice. Log questions and exponential questions come in a variety of different contexts. But try and sketch the graph. That helps you to see what's going on and to remember what values you can have and can't have. Use your calculator if you have it, if you're allowed it in the exam. If you're doing paper 2, do as much as you can on the calculator. I can't stress that enough. You need to really become best friends with your calculator. And any questions? I hope that made sense and helped with your understanding of exponents and logs. Biggest tip is don't let them scare you. They're just functions. So if you want these notes from this session and more past paper questions, just Instagram at Miss Ivy Maths, send me a DM, Miss Ivy Maths, with a DM, and send your email address, and I will share the folder with you that has all the session notes and tons of exam past paper questions with the mark scheme of all of these topics that we've covered so far. And then there's also the homework assignment. So yeah, if there are no questions, then I will stop there. And thank you very much for joining. I really hope it. And good luck with any studying that you are doing today and all your exams next week. And maybe see you later or tomorrow. Bye.